Okay, thank you very much. And thank you very much to the organizers for inviting me. As Caroline mentioned, this talk is very much going to be a continuation of hers. I'm going to start off with a theorem and then go into a sketch of a proof of a theorem. So I apologize for not sort of warming you up, as it were. So yeah, let's do it. So I'll remind you the main kind of definition from the last talk is this notion of a stable subset in a group. In this talk, I'm going to be looking at arbitrary finite groups. So let G be a group, and given some integer k greater than or equal to 1, again, it's the same definition. I take a subset A and I say it's k stable if sort of the binary relation, so I'm going to be referencing this, so y times x is in A, if this binary relation omits a half graph of size k. So there do not exist these A1 up through AK, B1 up through BK, so that the product AI times Bj is in this set if and only if I is less than or equal to j. Or saying this formula does not have the k order property. OK, good. And so you saw a theorem from the last talk about structure and regularity for stable subsets of finite dimensional vector spaces over prime fields. And this is going to be an analogous result with some tweaks for arbitrary finite groups. So, and I should say, so this is all joint work with Caroline, Terry, and Conant and Pillay. So the theorem says, for any k greater than or equal to 1 and epsilon greater than 0, I find this number n depending only on k and epsilon, so that if I take a finite group, G, and a subset A, which is k stable, then I find this normal subgroup, H, like in the last talk, whose index is bounded by this number n, and it satisfies the following properties. And so in fact, the first property I'm going to jump right into is right to the structural corollary that Caroline had in the last talk. In particular, I can find a subset G, Y of G, which is a union of cosets of this group H and looks almost like A, meaning the size of the symmetric difference with A is at most epsilon times the size of H. All right, and as Caroline pointed out, or said, getting this, I shouldn't point there, getting the size of H here is stronger than getting the size of G, which is what was in that corollary. And in particular, this improvement, I mean, it does a number of things, but what it allows us to do is actually deduce the regularity statement immediately from the structure statement. So immediately from that, I get that I have this regular behavior with respect to cosets of the subgroup H. For any coset, either the intersection with A is small, or the intersection with A is almost the whole coset. And this is immediate from 1, again, because I just take a coset and I ask, is it in the union Y? If it is, I get it's almost everything. If it's not, I get it's almost nothing, because of this slightly improved error here, epsilon times the size of H. And then, as someone asked in the last talk, we also get that H is somehow definable from the set A. In particular, it's a Boolean, in the Boolean algebra generated by translates of A. OK, and then another very important thing to say here is what do we not get? Well, most importantly, what we do not get is any information on this number n. We do not get polynomial bounds because of the method of proof that we're going to be doing is an ultra products proof. So there's definitely some trade-off here in terms of what we improve and what we can't get. Right, so I want to sketch the proof of this, and which I hope will be essentially accessible as long as you're somewhat comfortable with an ultra product. That's the only kind of explicit technology that you have to understand. And then the other thing is just a fact from stable group theory. Right, so I'm going to show you that fact. So now let G be a group, possibly infinite, and fix a subset A. And now what I'm going to show you is not interesting for finite groups. So you want to be thinking now infinite groups for a second. I mean, it's trivial for finite groups. It's not interesting. So here, and right, notation, let B sub A of G be the Boolean algebra generated by left translates of A. All right, I'm going to be referencing this a few times. This is some Boolean algebra of subsets of G. And now here's the fact. This is due to Hryshowski and Pillay. If I take a group G, and I take some subset of A, which is k stable for some k, and in this fact the k won't matter, just that we have this stability, then what can I find is a finite index subgroup H in this Boolean algebra generated by left translates of A, and a left invariant finitely additive probability measure on that Boolean algebra, which satisfies some properties. And the properties that we get is that this measure is the unique such measure on the Boolean algebra, namely it's the unique left invariant finitely additive probability measure restricted to this particular Boolean algebra generated by this stable set. And then the other important thing is that we get this sort of structural situation. In fact, for anything in the Boolean algebra, for any x in this Boolean algebra, if I look at the union of left cosets of the group H, call that y, and in particular I look at the left cosets whose intersection with the set I started with is big in the sense of having positive measure, then the set looks almost like that union. Sorry?
Yeah, the condition is just A is stable.
Yeah, but I didn't define that. So stable means k stable for some k. Again, the k does not show up in this. I just stable for some k. Good. So I'm getting this like, my sets look almost like unions of left cosets of this subgroup. And I can see exactly which cosets to take. And so this is the main fact that we're going to use. And now from this, we'll be able to prove the theorem I put on the first slide rather quickly, just using this sort of common method of ultraproducts of counterexamples. That's a good question. 1990 something. 96. It's from the, yeah, so it's from the paper.
It's deduced quickly from something in the paper on groups defining the local pseudofinite, Israel German.
Yeah.
So, follows from something about
so I should say you have to do a little bit of work to get it from there. It's in the, which is in our paper, but yeah.
So here you mean for every C, a union of left coset C, so C is a set of cosets, right?
So C is the left coset. If Y is the union of left cosets, call it C, left cosets of H, so whose Y is a union of cosets. It's not a set of cosets, it's a union of cosets. So it's a subset of the group. Yeah.
C is one coset? Or?
C is a coset, yes. Okay, any more questions about the statement? Yeah.
All such left cosets?
The union, I didn't write, yeah, the union of left cosets C, I'm calling it C. It's a left coset of H, and it satisfies the property that the intersection with X has positive measure. Take the union of all the left cosets of H satisfying that property, call that Y. It looks almost like X. Sorry if that, I'm sorry. So here we go. And now this is to confuse you. Okay. Good? All right. Sorry? Oh, snarky remark, that's cool. So yeah, this is the theorem we're going to prove. This is the same theorem from the first slide, so you don't have to reread everything, but I just put it up there again to remind you that we just have to prove one. The regularity statement is immediate from one. So I want to prove this now, or sketch the proof at least. So suppose the theorem fails. What does that mean? You have to go back and negate all the quantifiers and all that stuff. So we have a k greater than or equal to 1 and an epsilon greater than 0, so that for any number I can find a counterexample to the theorem, which I mean the following thing. I find a finite group Gi, a k-stable subset Ai of Gi, and it's a counterexample in the sense that this set Ai resists decomposition by any finite index subgroup of index at most I. And so I've written that there. If I take any normal subgroup of index at most I and any union of cosets of it, it doesn't look enough like A. Okay. So these are my counterexamples to the theorem. And I am going to do an ultraproduct. So I'm going to view each of these as a structure in the group language together with an extra unary predicate, naming this special subset AI. And then I'm also going to carry along measures with me so that mu I be the normalized counting measure on GI. Take the ultraproduct of these over some non-principal ultrafilter U, call that structure that I get G comma A, so naming the group G and then this predicate A, which is the ultraproduct of the AIs. And then I also get along this pseudofinite counting measure, mu. Good, so I have a group and I have a measure, and now I'm in the situation of applying that fact from the previous slide. And then, oh, because of course we have to note that since each AI is k-stable for the same k, doesn't matter what it is, but it's the same for all of them, by Wasch's theorem, A will be k-stable as well. It's a first-order property. Good, so now I'm going to use the Hrshovsky-Pillay fact. By this fact, I get, and I change the letter for an annoying reason, so I get a finite index subgroup K of G in this Boolean algebra generated by left translates of A. And I get some subset Y of G, which hopefully this is clear. It's a union of cosets of K, left cosets, I should say. such that the measure with respect to this unique measure from the Hrushkovsky-Pillay fact of the symmetric difference of A and Y is 0. Okay, so this is what the theorem tells me. I just changed H to K. Good? And so why did I change H to K? Well, annoyingly, the fact, or at least from the work, it doesn't tell us that this subgroup is normal. But there's an easy way to, oh, sorry, before we get to that, the other important thing from the fact is that that measure was unique. And so the pseudofinite counting measure satisfies those properties. It's left invariant, finitely additive. So restricted to this Boolean algebra, BA of G, it agrees. And so the pseudofinite counting measure says that the measure of the symmetric difference of A and Y is 0.
Recall this theorem. Why we have this measure 0?
Uh, 0. I get measure 0 plus the measure's unique.
But what's the context? What about the assumption? Why is it?
I'm in a group and I have a k-stable subset. So yeah, it's a few assumptions to get this to work. Yeah. Okay, and so this unique measure is 0, and so the pseudofinite counting measure is also 0. And so now I'm going to fix the problem I was saying before. I want a normal subgroup for the theorem, and there's an easy way to fix that. I just take the intersection of all conjugates of k. It's still definable now from left and right translates, and it has finite index still, index at most factorial of the index of k, and it's smaller. So if y is a union of cosets of k, then it's a union of cosets of h. So I just do this minor thing to get a normal subgroup. And then the measure is still 0. It's the same set. Measure here is 0. And I'm making this note that that's strictly less than epsilon over n, where n is the index of h. And why am I making that note? Well, because it's true and because it's something I can bring down in ultra product. Measure 0 I can't bring down so well, but measure strictly less than epsilon over n I can bring down. And so that's what we're going to do. H is an ultra product of some hi's. Y is an ultra product of some yi's. And by Wasch's theorem, this property in the previous paragraph happens for an ultrafilter many set of indices, in particular arbitrarily large. In particular, I find this index I at least bigger than n, so that hi is a normal subgroup of gi of index n, yi is a union of cosets of hi, and the measure is strictly less than epsilon over n. Okay, so I can't pull measure 0, but I can pull measure strictly less than epsilon over n. So you have to do some formalism here to make statements about the measure, et cetera, et cetera, et cetera, but it's possible, and this is the idea. And this contradicts our choice of these counterexamples. All right, so it's done. Any questions about the proof? Fantastic. Okay, so good. So I'm going to move on from this and move toward the NIP case, and that's what I'm spending most of the talk on, is the NIP case. And I'm going to define NIP, and then I have half the slide here motivating why study NIP, but someone already asked about it, so I guess I don't need to motivate it anymore because it's already interesting, so that's good. But all right, but maybe everybody doesn't know what NIP means. I'm going to define it for sets of groups here again, not like a general definition. So let G be a group. Given k, integer k greater than or equal to 1, I said, say that a set A is k NIP, so think an analogy to the definition of k-stable. It's k NIP if I omit some kind of combinatorial pattern, like the stability case. But here the combinatorial pattern is sort of a coding of arbitrary subsets of the numbers 1 through k. Specifically, I cannot find elements of the group A1 up through AK, and then other elements B that are indexed by subsets of 1 through K, not by 1 through K, but by subsets of 1 through K, B sub x, such that the product AI times BX is in the set if and only if I is in X. So now instead of coding this like order half graph configuration, I'm coding subsets of the numbers from 1 through K with this same formula here. Okay. So again, why study this? Well, because she asked about it, so that's why. No. So it's a generalization of being stable, so that's one thing. You can think about that as an exercise. K-stable implies K NIP. And then it's also, this notion of being NIP goes by a lot of names. A subset is, you can check, is K NIP if and only if this set system of left translates of A has VC dimension strictly less than K. So if you're familiar with VC dimension, that might be a nicer definition of K NIP for you if you like. The stable regularity lemmas for graphs have been extended to the NIP setting with great success, so that makes you think that you should be able to do the same for these kind of algebraic or arithmetic regularity lemmas. And there's also a lot of tools available. So measures on definable sets in NIP theories, especially invariant measures in groups in definable and NIP theories. There's a lot of machinery there and a lot of tools that's been developed over the past 15 or 20 years or something like that. Good. And so what's the goal? Well, the goal is something kind of, like what Caroline was talking, what I've been talking about is we want a regularity theorem for NIP subsets of groups, which is somehow improved from what you would get if you just applied graph regularity to the Cayley graph. In particular, incorporating the algebraic structure in some meaningful way, like partitioning your set with cosets of a subgroup and things like that. And actually, there's more you can get into. I'm kind of just chasing back a thought. Going into the stable case, you can say somehow even stronger things about partitioning up your Cayley graph using this subgroup that you might not get from just having a graph. And beyond these epsilon goodness, and a question about epsilon excellence, I think, comes up. So there's a lot to investigate there. And the other thing I probably should say here, I'm not going to go so much more into translating it to graphs. Caroline did a lot of that in her talk. But in this situation, the Cayley graph is not quite as workable because the group may not be abelian. But what you can do is take your set G, or your group G, your subset, and look at like a bipartite graph where you've got a copy of G on both sides, and then you put an edge between X and Y if X times Y is in A, say. And then this arithmetic regularity with a coset of a subgroup gives you extremely nice, almost like a complete description of this graph in some sense, if you really get into it. But that's probably the most I'm going to say about translating this to graphs. Good. So this is the goal for NIP. And I think the next slide is to show you one thing that we've gotten very recently, which is not a completely general statement. I'm going to talk a little bit about the general statement, hopefully if I have time at the end. But it's a very nice statement for groups of bounded exponent, which has something to do with the generalization that Caroline mentioned by Alon, Fox, and Zhao, but I'll mention that at the end. So it's a generalization of their theorem, so I'll say why in a second. So this is what we get. For any integers k and r greater than or equal to 1, so I'm adding this extra integer r, which is going to be a bound on the exponent of the group, I find a number n, depending on this data, such that the following holds. And now it's going to look a lot like the stable regularity theorem, but with some slight tweaks. So I take a finite group of exponent r and a subset A, which is k and IP. And what do I get? I get a subgroup H, like in the stable case, a normal subgroup H. Oh, I didn't write normal, but it is normal, of index at most n. But then I also get this error set, which I'll explain, this error set GE, subset of G coming in, satisfying the following properties. So first thing is that this E is this error set. It's a union of cosets of H, but it has kind of small size. Its size is at most epsilon times the size of G. And then the rest of it is basically what happens in the stable case, the structure and the regularity, if you ignore the error set. And so what do I mean by that? We get a structure statement. There is a subset Y, which is a union of cosets of H, such that it looks like A in the same way if I throw away the error set. If A prime is A, subtract this error set, then the symmetric difference of A prime and this union of cosets has size at most epsilon times the size of H. And this gives us this nice strong bound that allows you to then deduce a regularity statement. If you take a coset of E, which is not in this bad set, this error set E, then either it intersects the set A in almost nothing or almost everything. So it's just like in the stable case, except we introduce a union of cosets, which is kind of the bad or irregular elements, and it works for groups of bounded exponent only. And I'm going to say hopefully more about that in the rest of the talk. And then I should importantly say that, oh yeah, it's definable in the same way. And importantly, this generalizes, but without getting the nice polynomial bounds. It generalizes this very recent, and they were building off work that they had seen Caroline Terry and Julia Wolf do, and they released for bounded exponent, but also abelian. So, and I should say the methods are, we've been working on this, the methods are disjoint, where we prove this with an ultra product statement again, and all that. Yeah?
Is a small error necessary or just an artifact?
It should be, I think it should be necessary, because if you removed it, you would get the stable regularity statement, and I think you can find subsets that have bounded VC dimension but are not stable or something like, or Yeah, okay, that wasn't a very sensible answer, but I bet it's necessary. You could find examples. The bounded exponent is a necessary assumption to get this subgroup, and I'm going to say something about that later. So, good. Okay, so the goal for the rest of the talk is to show you some of what we had to do to prove something like this, and what we're obtaining in the general case, where I remove the bounded exponent assumption, and where we're going with that. It's going to be now model theoretic tools being developed, so if you please ask questions if you have any. All right. So the main thing, how do we prove a theorem like this? Well, for the stable case, we took an ultra product of counterexamples and applied this fact. It's the same fact from before. You don't need to read it again. So I had this fact from the literature that I could just hit with the ultra product with and be done. And so the main now barrier is that is not so clear cut for the NIP case, what the fact should be. What is the analog of this? Oh, that's a spoiler alert. So I should say, though, that if you tried to pursue this kind of fact for general NIP subsets of groups, it wouldn't work. You're not going to get this like unique measure all the time, and you're not going to get all this stuff. But the other observation is that we didn't apply this fact just to any old group. We applied it to an ultra product of finite groups, or a pseudofinite group. Okay, so not just some arbitrary group. So in the proof above, we applied this fact to the case that G is a pseudofinite group. And so the rest of the talk is going to restrict to pseudofinite groups, and we will obtain nice results there. Good. So now I'm going to be fixing some assumptions for the rest of the lecture. So for the rest of the talk, L is a first-order language, expanding the language of groups. If you don't want to think so much about the general stuff, you can think about L being the language of groups with like an extra predicate for a distinguished subset, because that's the case that we apply this thing when we're looking at these things. But it could be any structure you want, expanding the language of groups. And then I'm going to have a collection of finite L structures, each of which interprets the group structure as a group and then has this extra stuff on it. And for simplicity, you can think each one is just like given a distinguished subset, if you like. And then I'm going to take G to be a highly saturated elementary extension of an ultra product of these structures. Okay, so I'm going to take an ultra product of the finite structure, and then I'm going to go to a monster model, to use terminology a lot of us are familiar with, and I'm going to work there. So it's a very saturated elementary extension, but you can think of it just kind of like the ultra product if you want for most purposes. Good, and then I have a pseudo-finite counting measure arising from the counting measures on the finite structures in the same way, and I can lift that to the saturated extension. So this is what we're going to use for the rest of the talk. And then sort of a nice observation to make here for people who are more familiar with the terminology is this. If I were to assume that the whole theory of this structure were NIP, which means every definable relation is NIP, I'm not going to want to do this in the talk. I'm not going to work with this assumption. But if I were to assume this, then from the VC theorem, you could very quickly prove that this measure is what is called definable and finitely satisfiable in a small model. Okay, so that, I'm not going to define those words in blue because they're not so important. I'm going to say analogs of them later. Yeah?
Are you getting the measure on the monster?
Adding extra functions and structure. Same way you extend a Kiesler measure to a bigger structure, any way you like. For every formula, I add a function to 0, 1 that tells me the measure, and then I extend. So yeah, there's NIP papers, NIP1, NIP2, NIP3 that have a lot of this stuff developed in them, which are good to read. Yeah. No, that's not a hand. Sorry. Okay. Sorry. Okay, so going back to this proposition, this is not going to be an important proposition for the rest of the talk. You can ignore it. But if you're familiar with it, you know that if you have a Kiesler measure in a group, or say an NIP group or whatever, having these properties, whatever they mean, it gives you a lot more. It's a lot more like stability. And so we're motivated by this. We're going to be trying to find this behavior, but in the local case, where I don't assume the whole structure is NIP, but instead assume I'm just working around this particular NIP subset or formula, it will be the general situation. Okay, so that's just some like a motivational observation. And now I have to go through kind of a slide of terminology. So some of it will be important to remember, not all of it. I hope most of it's familiar. So I'm going to let delta x y bar be some formula in my language. And again, you can think about like this formula where say A is definable, or you have a predicate naming it or something like that. If you want to think about it that way, it's fine. But you can work with any formula here for these notions. B sub delta of G is going to be the Boolean algebra of so-called delta formulas over G, which are just formulas generated by instances of delta, where I plug in things for the parameters y. And so in this case, plug in something for y, move it over. It's a left translative A, so it's like the same Boolean algebra from before. Good. And then I'm going to have S sub delta of G as the space of delta types over G, and these are also known as ultrafilters in this Boolean algebra. I'm going to call a type weakly random. I think this is the right terminology, but I'm going to call it weakly random for this measure mu if the measure of every formula in it is positive. And this is some kind of notion of like being generic. And then also I'm going to work with a stabilizer type. So given a type P, the stabilizer of P is the set of group elements in G that fix P. If I multiply all the sets on the left by G, I get the same type back, or all the formulas, if you like. I'm going to work with a final notion of stabilizer, which is that if I have a delta formula phi, epsilon greater than 0, I'm going to have the epsilon stabilizer of the formula is the set of group elements that don't move the formula very much, in the sense that the measure of the symmetric difference of sort of multiplying the formula on the left by G and the original formula itself is small. So I multiply by G, and it doesn't move the set that's defined very much. All right, so I apologize for this full slide of terminology. I'm going to repeat some of the assumptions in a second that you have to remember, but the ideas are I have definable sets, delta formulas, types, which are ultrafilters. I have these notions of weakly random types, which are types where all the formulas have positive measure. And then I have two ways of stabilizing things, stabilize a type or stabilize a formula up to epsilon. Good. Yeah, so repeating the context. Now, for everything I say for the rest of the talk, G is a pseudofinite expansion of a group. Just to repeat, this is very important for everything I say. It would not work in general. It's a pseudofinite expansion of a group. And I'm going to work with a formula through the whole talk, delta x y bar, which I'm going to assume is NIP, k NIP for some k. And again, the k won't really matter. And I've rewritten the definition of what that means there. It's the same definition as what I said for this formula before. It's just that I have an x and then I have some tuple of parameters y bar. But it basically says that the instances of this formula have VC dimensions strictly less than k. So I'm going to assume that for the rest of the talk. I'm also going to make this technical assumption that the set of delta formulas is invariant under left multiplication. And so this is just to make sense of doing, like, so that I actually get an action on the type space by multiplication by G. And so this is, you would call the formula equivariant or something like that if this happens, but this is what it means. If I take an instance of delta and multiply on the left, it's equivalent to some other instance of delta. And if you think about like this kind of thing has this property. If I multiply x on the left by something, so if I have, some a and then I multiply x on the left, well, it's just the same thing as multiplying or sticking in some parameter a times c. Yeah? So that's, yeah, I mean, that's what the bullet before it says. The family delta. Yeah, yes. The family is NIP. The family of instances of delta has VC dimension finite. Yeah. OK, so again, this allows me to like multiply things on the left and be back where I started and not have to worry about it. And it's always holds if you're looking at like this kind of case. But sort of annoyingly enough, I'm also going to care about multiplying on the right. And I don't want to assume that I have this kind of invariance under right multiplication, but I am going to have to like pay attention to it. And so in particular, I'm really going to be mostly working around a different formula, delta r, that kind of allows me to multiply on the right. So delta r x, where now I have another parameter. In addition to y, I have a u. It denotes the formula where I just multiply on the right. And so in this case, it's getting a little messy. I'll erase. In this case, if this is my delta formula, my delta r formula would be yxu is in A, where x is the variable and y and u are parameters. All right. So talking about bitranslates. Why the letter r? Because I multiply on the right. Yeah, it's random. Feel free to suggest something different. I can't change it, but I'm not saying this is NIP, and in fact, it need not be. It could be anything. It could have strict order property, independence, TP2, whatever you want. So it need not be NIP, but it's going to be NIP enough. Like instances of it are going to have some NIP flavor to them that will allow me to make this work. But yeah, I mean, you could just assume that this formula is NIP and like, okay, if the group's abelian or something like that, then it would be fine. But we don't want to do that. Okay, good. All right. And then now finally, I'm going to define a thing. It's going to be a special subset of the group G. It's going to be the intersection of all stabilizers of all delta R formulas for all epsilon. So intersect all the stabilizers, everything, okay? But I'm working over delta R formulas now. So I'm allowing Boolean combinations of delta R multiplying on the right and stuff. And I call this G00 delta R. As Caroline said, I didn't pick this nomenclature. Well, I kind of did, but motivated by other stuff, so G00. Sorry?
Mu or delta R formulas is definable and fact definable?
Yes.
But then you need delta R to be NIP to move up.
Well, locally, no, you don't. I mean, so, well, okay, if you get the right, if you formulate exactly the right definable, finitely satisfiable that I mean.
It's not the C class and work out with.
Yeah, so it's probably not definable. It's not definable in the way you're thinking. It's definable in a different way, which I'm not actually going to get into. So basically, if I take a delta R formula phi x with parameters multiplied on the right or whatever, and then I look at this as a new formula with just a single x and a single y, this is definable, finitely satisfiable, and that's all we need to make it work. So you're right, but yeah. Yeah, separately, right, and that's all we need. So yeah, it was very careful to make this go through. Well, to make what go through? To make the next theorem. Okay, but I'm going to try to avoid these kinds of things, but yeah. Right, so this is the first main theorem. So for any delta R formula phi and any epsilon greater than 0, the epsilon stabilizer of phi is, okay, delta R type definable. Two things, I'm going to do them both. It means it's an intersection of a small number of delta R formulas, where small means less than the size of this monster model G. And it's also generic, which means finitely many left translates cover the whole group. This was called syndetic in an earlier talk. And he said, we model theorists call it generic, and here you go. So. Okay, so this is like the definable, finitely satisfiable, but I'm not, again, not explicitly getting the details, but like we've got this definability thing, and then this genericity comes from a finite satisfiability type thing, but kind of one formula at a time. All right, and so then what I get is that the intersection of all of these stabilizers, which I was calling G00 delta R, is a delta R type definable subgroup of G of small index. Bounded means less than the size of G, which is what you might expect based on the notation, and if you're familiar with the NIP work. And it's also the stabilizer of any weakly random delta R type, which is important. That's important for some of the inner mechanics of the theorems I'm going to say, and it won't be so explicit, but one thing you can prove as a corollary of this if you work with it is that it's a normal subgroup, which is also helpful. And, okay. So these are the main things, but what do you have to remember? You basically just have to remember that we get this delta R type definable subgroup of small index, and it's normal. You don't really have to remember A and C so much to understand the rest of the statements. But now we've got this sort of canonical type subgroup, which is like it's playing the role of the subgroup from the Hrušovský-Pillay fact earlier, that H that we got. This is sort of the new object playing that kind of role. Okay, and so then we're going to go try to get basically the things from that Hrušovský-Pillay fact. The Hrušovský-Pillay fact gave us this subgroup, which we now kind of have the thing acting like that, this G00. It also gave us a unique measure, and then it gave us this structure for sets in the Boolean algebra. And so those are the next two things to get at. So the uniqueness of measure I'm just going to state and not say much about. This measure is the unique mu, a pseudofinite counting measure, is the unique left variant finitely additive probability measure on this Boolean algebra of delta R formulas. Okay, and so unlike the previous theorem, which was more just kind of nitty-gritty, going through all the steps and using ideas and making it work, this theorem is modeled definitely off of a lot of previous work. So I'm just going to say what some of the ingredients are. Okay, we need the previous results about this G00 delta R, even though it's not making an explicit appearance in the statement, but we use it. We use a sort of standard kind of like approximation of Kiesler measures using average measures over some notion of a generic type, which in this case is like the weakly random types, and you go and localize stuff from Hrušovský-Pillay. So, I mean, this is mostly just a shout-out part, giving due acknowledgement. So we use something called Borel definability of invariant phi types, local types, which is due to Pierre-Simon. And then we also go through and sort of localize, very explicitly, several results from a recent paper by Artem Chernikov and Pierre-Simon on definably amenable NIP groups. So they work with a definably amenable group in an NIP theory, and if you go through, you can see a lot of the steps localized in this particular setting to get what you want for this unique measure. Okay, so that's good. We have our unique measure. And then the last thing, this structure, the last thing from the Hrušovský-Pillay fact was that anything in the Boolean algebra looked basically like a union of cosets of our special subgroup. And we're not going to get that first. What we're going to get is a regularity type statement first. So we saw before how, at least in this infinite setting where close means measure 0, being almost a union of cosets of a subgroup means that you're sort of regular with respect to cosets of that subgroup and back and forth. And so we're going to get this statement now that looks very much like regularity, although it's in the literature under the phrase generic compact domination. And it's kind of quite remarkable that this sort of behavior goes back to just like 2004 or something with some of the O-minimal conjectures of Pillay and then have been developed in a lot of contexts. And as you'll see as I put it up here, it's very much a regularity statement like what we've been seeing. Okay, but what do we have to do to give the statement? Well, we have to work with the quotient group, G mod G00 delta R. Okay, it was a normal subgroup, so I get a quotient group, but the important fact is there's a natural topology on this quotient group called the logic topology. I've defined it there, what it means for a set to be closed. What the actual definition is not so, so a set's closed if the pullback to the group is type definable. That actual definition isn't so important. The important thing is that we just have this topology on the quotient. Not so important for the statements. And the group being bounded index is extremely important for this to make sense. So otherwise that seems kind of like a weird thing. But okay, so now we've got a compact Hausdorff group, G mod G00. And what do? I take a delta R formula phi of x, so some Boolean combination instances of delta R, and I'm going to define this error set. It's going to be like the irregular cosets or the bad cosets, E sub phi of x. It's the set of cosets of G00, which, okay, what I've written here is something, but what it means is that this coset intersects phi and its complement, so intersects this set and its complement in kind of a big way. Where now in a big way means I find these weakly random types P and Q, which are kind of big because all the formulas in them have positive measure, and one of them has everything to define the intersection of the coset with phi, and the other one has everything to define the intersection of the coset with not phi. So it's like a regularity statement. This coset is bad. It's breaking up, or phi and not phi are breaking it up into two big pieces. And so the theorem, the generic compact domination theorem, says that if you have a delta R formula phi, this set of errors is small. In particular, has Haar measure 0. So the compact group, so we've got the Haar measure, and the Haar measure of this set is 0. So it's like saying few irregular elements, like in the same way, but all up in this pseudofinite infinite setting, and we have to pull it back down. And that's now really the rest of the work in the project, is how to pull this back down to finite groups. And not everything that I've said here is first order, and what does it exactly say? It's not as clear-cut as in the stable case. And this was similar to the previous theorem. The proof requires this uniqueness of the measure in some way, more work of Pierre-Simon, and then more adaptations of proofs from this same paper by Artem and Pierre on definably amenable NIP groups, which are going back to ideas from NIP2, NIP3, which is Hrušovský, Pillay, Petersil, and Pierre all together with those three papers. Okay. All right, so again, the point is that if I'm in this kind of NIP setting, and I have some set, this like phi of x is like a definable set, and then I have this subgroup, and the bad cosets for the definable set have kind of small measure. There aren't very many of them, to say things in a very informal way. Right, and so how can we get this? So now you have to think back. So I gave you this theorem about bounded exponent. How can we apply this to get that theorem? Well, I'll tell you now. So this is going to be a special case that will relate to this bounded exponent assumption. In particular, I'm going to make this big assumption, which does not hold in general. This is, as far as I know, this is a big assumption. I'm going to assume that, all right, G00 delta R. I told you it was delta R type definable, which means it's an intersection of delta R formulas, few of them. I'm going to assume it's actually an intersection of delta R definable groups, so, which is not immediate, and it doesn't always happen. But if I make this assumption, then I can get a nice theorem. Okay, so make this assumption now, add this to the context for a minute, and we get kind of an analog of the Hrushevsky-Pillay fact upstairs in this pseudofinite group, which we'll be able to pull downstairs through an ultraproducts argument to get the bounded exponent theorem. And what it says is that if I have a delta R definable set X, and I fix some epsilon bigger than 0, then I can find a delta R definable finite index normal subgroup H, this object that I want, this finite index normal subgroup, and a subset E, which is going to be like my error set, satisfying the properties that I want, but now up in this upstairs setting. So E is a union of cosets of my group, and it has small measures, so it's like this small set of errors. And all of the cosets of this subgroup, other than the ones in this bad set, are what was Caroline calling like epsilon good for the thing, although it's like 0 good here because we're in this infinite setting. So if I take any coset of this normal subgroup H that's not in my bad set E, then either it intersects C in almost nothing, meaning the measure 0, or it intersects C in almost everything, meaning the measure of the complement is 0. Okay, and then again, immediately from this you get the regularity. Or no, that is the regularity. Immediately from this you get the structure. If you take X prime to be X throwing away the error set, and okay, maybe here it's a bit clearer than at the beginning. I take the union of cosets that don't intersect the bad set, but intersect my set X in positive measure. That union of cosets of H looks almost like X after I throw away the errors. All right. So it's got all the ingredients that we want a bit to unpack. But getting these definable groups here definitely very much depends on this assumption here, which does not always hold. This assumption is important. But one thing that you can prove, a small argument, is that if G has bounded exponent, then we get this assumption. G00 is an intersection of definable groups. It's not trivial. It uses something. It's not long, but it's true. Okay, and so then I'm not going to go through another ultraproduct example, but with this theorem, you can then just do the same proof to get the bounded exponent case in IP. Assume the finitary theorem fails, take your counterexamples, take their ultraproduct. It will have bounded index, so it will be here. Apply this and pull it back down, and you get the theorem. Okay. Good. And so what about getting rid of this assumption? Well, you can't get rid of it in general. There are counterexamples, or there are examples in this Alone, Fox, and Zhou paper that show that for NIP sets, you can't always expect to get subgroups all the time. And so now the question is, what in general, if we don't make this assumption at the top, what are we going to get instead of a subgroup, a finite index subgroup? Yeah. Okay, well, I mean, the need to go to the monster was just to define things. We have this type definable set. There's also one instance of Erdős-Rado to assume. So maybe you can get rid of it, I don't know. But I mean, just to be extremely flexible with working with everything. And although there is one explicit instance of Erdős-Rado that might cause an issue, but yeah. Okay. Good. So yeah. So now in the last couple slides, I'm going to tell you what we're doing at the moment to get rid of this assumption and replace finite index subgroups with something else. It's things that kind of look like so-called Bohr sets. So here's a lemma we can prove. Without this assumption, so back in our same context of everything, but no longer making this assumption that G00 is an intersection of groups, I can find delta R definable sets, countably many of them BI, so that G00 is an intersection of these. But instead of being finite index subgroups, which I can't always get, instead they're kind of like, the slogan here is like a Bohr set inside of a finite index subgroup, which specifically what I mean is that for each I, for every one of these bi's, I can find a finite index normal subgroup H, should call it like HI or something. And I can find, ignore delta R definable, I can find a surjective homomorphism from that subgroup H to some n-dimensional torus for some n. And I can find an identity neighborhood inside of the torus U so that this BI contains the pullback of the identity neighborhood and is inside this finite index subgroup. And this may not look so interesting if you haven't looked at stuff like this, but this is in the sort of infinite group setting what you might call like a Bohr set. It's a subset that contains the pullback of an identity neighborhood under a homomorphism to a compact group, say in the full generality or something like that. And so we can get this. We can get this in the upstairs case. This uses some stuff. It uses commutativity of the connected component of the identity in this compact group here, G mod G00, which very much depends on the group being pseudofinite again. This is a result about pseudofinite groups that was, I mean, basically unimproved enough that we need for this case, and then it was generalized by Nikolai Schneider and Tom. And then we use the structure theorem for compact groups as projective limits of Lie groups. And so the commutativity plus Lie group is where these toruses are showing up. OK, so we get this structure upstairs, which in Bohr sets are sort of often used in additive combinatorics. I'm only just now getting familiar with this stuff, so I'm not an expert at all. But my understanding is they are often used in additive combinatorics as replacements for subgroups. If you don't have a lot of subgroups around, you look to work with Bohr sets because they kind of have a lot of nice structure. In particular, they're big. They're generic. They're going to be like approximate groups also. Or something they contain the identity and stuff like that. I don't know. So anyway, there are these interesting ingredients, which I'm hoping to learn more about. And so now in progress, we haven't quite finished it, so I didn't want to lie to you, but it's almost done. We need to make a statement about this that we can pull down through an ultra product. And so I'll just put it all up. So what we're getting is basically the same statement as like the bounded exponent case or the G00 is an intersection of groups case. Basically the same statement. If I fix a definable set X and an epsilon, then I can find my delta R definable sets B and E. E is still going to be like an error set, and B is going to be replacing the finite index subgroup from before. And so it's going to do what I want. E is going to be a small error set. And it's also going to have this regularity property with respect to translates of B, which used to be cosets of this finite index subgroup, but now they're just translates of this Bohr set. But they still have this kind of regularity property. If I take anything not in the errors and I translate B, either it intersects X and almost nothing or almost everything. And then again, these aren't just random definable sets. They're these kind of Bohr sets inside of finite index subgroups. And I've just repeated the things from the lemma there. Yeah.
What does it mean for pi to be definable?
Yeah, so it means that the inverse image of any closed set is type definable. Yeah. Right? Yeah.
It's a continuous logic formula with values in the compact group rather than groups.
I was going to say that too. OK, so then just to finish up here, once we finish this, this is what we're working on during this wonderful program. Once we finish this, it will pull down to an NIP regularity lemma, which I'm not going to state now. I'm out of time. But an NIP regularity, we're going to pull it down to the finite group setting without this bounded exponent assumption. And instead of finite index subgroups, we'll have these so-called, unfortunately, like approximate, oh, I didn't even spell it right, approximate Bohr sets, where this is even approximately the right word. And the approximation comes in from the fact that we can basically pull everything down in here except for saying something exactly as a homomorphism. And so we're going to have like almost a homomorphism up to some small error. And then we're going to work with that, and it's going to be great. So that's the end of the talk. Thank you very much. What we're really working with is a lot of formulas that have the property that this is NIP. Like, so the family of translates of the formulas is NIP. That's really all that you need. You don't need so much, yeah, you don't.
A, B, where B delta are definable.
Yeah, so that will be delta R definable because delta R is still invariant under left. Yeah, yeah. For a specific instance of a delta R definable set, a left translate will again be delta R definable. Yes, yeah. 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 Yeah, so actually, okay, I almost forgot to do this. So Anand's speaking in the model theory seminar on Monday, and he's going to continue and talk about stuff about around distality and more stuff around like a global assumption of NIP and that. But there are things you can say. So since, you know, for me, distality is still kind of a global assumption. It's a global situation, but you can say interesting things, and Anand will say them on Monday. And so I hear rumors about a local version of distality that could turn into something nice there. Yeah. Yeah, so I mean, there's work to do to understand exactly this approximation of a Bohr set. What exactly does that mean? And yeah, I mean, there's no reason that they would because they're not a subgroup. So we haven't, or at least I haven't looked at what does this actually mean in terms of partitioning the Cayley graph. I don't know, but my understanding is that in kind of the general arithmetic regularity lemmas, not in finite dimensional vector spaces, they're also about Bohr sets in the finite setting. So maybe there's stuff that I don't know about this that you can do, and so I'm really happy to be here again.
Is there a question over there? Yeah.
So in the finite version, you're getting these like approximations for almost Bohr sets.
Yeah.
Then there are counterexamples showing that you can look for subgroups, so the counterexamples say you can look for actual Bohr sets.
No, so this is, you know, it's possible we can get exactly Bohr sets. I mean, we have to keep working. So, but I mean, there is this, well, okay, but this regularity lemma, is it for arbitrary abelian groups or, yeah? Yeah. The green one? Finite abelian groups, yeah, finite. So there is an arithmetic regularity lemma for arbitrary finite abelian groups, which my understanding involves Bohr sets. So, you know, hopefully the idea is that since that kind of thing holds in the general abelian setting, you know, Bohr sets are like the worst you would get. And so if we add more stuff like NIP stable or whatever, we can just improve from there. So hopefully it's, the answer to your question is yes or no, depending on how you phrased it originally.
Any more questions?
Thank you.